to live up to it, don't I?
Yeah.
Anyway, so what I'd like to talk about today is regulating the plasma and galaxy cluster cores. And so this is work that I've done primarily with Greg Meeks, who's a grad student at Michigan State, Britton Smith, a former postdoc of mine, and Mark Voigt, who's a colleague of mine at Michigan State. And so I'd also like to thank Christoph for providing basically my whole introduction. So that was very, very helpful, so I'm probably not going to run over. But a couple key points, right? So galaxy clusters are these absolutely massive virialized objects, and they're a great example of galaxy evolution in an extreme environment. And so, most of the galaxies in them are early, the large galaxies are, many of them are early type. There's this radial dependence on the type that's pretty interesting, but who cares about the galaxies? The thing that's interesting to me is the stuff that's in between the galaxies, which is this really hot intercluster medium, and that's about 85% of the baryonic mass of the cluster. And as Christoph described earlier, it's very hot, it's very diffuse, it's full of cosmic rays, it's full of magnetic fields. It makes it sort of a fun plasma environment. And then we have this issue of clusters generally falling into two general types when you look at them in the X-ray. There's a cool core cluster, which are these three, and then there are non-cool core clusters, which look a lot more like this. And the cool core clusters tend to radiate really intensely in the X-ray by an order of magnitude or two more than a non-cool core cluster of the equivalent mass. And so that presents some real challenges when you're doing surveys of clusters, which is something I spend a lot of time worrying about. But for the purposes of this conference, there's a bigger problem, and that's that the cooling time at the center of this cluster, of these cool core clusters, is incredibly short. And so this is from Peterson and Fabian, and what they did is for a sample of clusters, they plotted the estimated cooling time as a function of radius, and there is a Hubble time, there's a gigayear, and in the central 10, 20, 30 kiloparsecs, for these types of clusters, the cooling time is incredibly short. And so that's weird, because this should radiate all of its energy away. And furthermore, it should form stars at some, if it's cooling and condensing, and truly condensing, it should be forming stars in the brightest central cluster galaxy at the rate of hundreds or thousands of solar masses a year or something like that. But there's very little evidence for that, certainly not for star formation at that prodigious rate, and there's very little evidence for gas at below about a third of the virial temperature, or at least lots and lots of gas. So something is clearly heating the plasma in the center of the cluster. And so here's a laundry list of lots of different ways. And probably, Christoph talked about some of these. I'm going to talk about a couple of these. In reality, it's probably a combination of many of these. But maybe something has to dominate. In order for us to actually approach this, we have to pick something. And so I've been worrying about AGN, which appear to provide lots of energy. And so, of course, here's this beautiful picture in X-ray, radio, and optical of an AGN by Brian McNamara. And then here's a plot that I think is roughly the same plot Christoph showed earlier, where here is the emission of the ICM, so the luminosity, the X-ray luminosity, or the rate of cooling. And then here is the power dumped into cavities, the estimated power dumped into cavities by the AGN, so the radio power more or less. And that's, this is the one-to-one line right here. And so plenty of energy is being dumped into these galaxy clusters by AGN, and that's fine. So that's probably the bulk of the solution. But how does the AGN turn on and off? What's going on there? Well, there's this very important clue. The cluster entropy, so this is a plot from Cavagnolo et al. 2008, where what they're showing is the central entropy of the cluster, where we're just defining it as T electron density to the minus 2/3. On the x-axis, central entropy of the cluster. On the y-axis, it's the radio emission coming from the central galaxy, presumably the AGN. And above about 30 keV centimeters squared, essentially what you see are mostly upper limits. And below that, it's mostly quite a bit of radioactivity. So something is going on. There is a central radio source if the central entropy of the cluster is low enough. So if the temperature is low enough, or the density is high enough, or some combination of those. And so what I'm curious about is how does that entropy, or how does that AGN get triggered? You need to develop cold gas in the center of the cluster, but it can't be a runaway process, because then you'd see tons of cold gas, there would be star formation, you'd see all sorts of emission. There needs to be some sort of regulation. So maybe there needs to be some sort of regulated multi-phase medium. And so the question I'm trying to approach here is essentially, what could generate this multiphase medium and what could regulate it. And I would say a stable multiphase medium, but I don't think that there's really any evidence that it's stable. But what regulates this medium, or what creates this medium that feeds the AGN? And so there's a bunch of possibilities, and I want to investigate conduction. Christoph mentioned it, but I'd like to talk about it a little bit further. And then I'd like to talk about a broader explanation of thermal feedback in cluster cores. So essentially, Frank, what did you say yesterday? The anything goes? Anything goes now hypothesis? So I want to talk about that a little bit. So first off, let's talk about thermal conduction. So first off, we know that hot plasmas conduct heat by electron transport. Fine. Magnetic fields complicate this issue. The more tangled your magnetic fields, the slower conduction occurs, but the basic principle is fine. Here's a plot from Voigt et al., 2008, where what they're showing is that cluster entropy as a function of radius for a bunch of clusters. And the blue lines are for clusters that are forming stars, or in the central galaxy. The red lines are for clusters that are not forming stars. And so what you see is that there is some dividing line between clusters that are forming stars and aren't forming stars. And so Mark did this really nice analysis where he looked at the field length and compared it to the cooling rate and came up with this criteria to relate the size of the region that should be able to cool, so essentially be thermally unstable, where cooling, radiating energy away, dominates heat flowing in via conduction, and then regions that are conductively stabilized where your cooling is where the cooling is dominated by the conduction. And so this is a really nice model. You can work it out on a piece of paper. And in principle, this completely dominates and explains everything. And so that's great in one dimension, but what about 3D? And so Mark asked me this question, and I said, well, I have I'm a simulator. I'm one of the authors of the ENSO code. I have a gigantic hammer with which we can whack this problem, and let's see what happens. And so what we decided to do was try to understand in cosmological simulations what the effect of conduction is. And this is actually a pretty challenging problem because the gas is very hot, the dynamical range is very long, it's computationally expensive. Not a lot of people have actually chosen to do this in cosmological simulations because it's sort of a pain in the ass. And so, this represented about a year and a half of my postdoc Britain's life, unfortunately. But what we did was several simulations of cluster formation. We picked 10 individual galaxy clusters from a very large simulation volume, reran them at higher resolution, sort of the standard zoom-in technique. All of those clusters were between 4 and 9 times 10 to the 14 solar masses. And we did this with a lot of physics, gravity, hydro, radiative cooling using metal cooling, star formation and thermal feedback. And we didn't put AGN into this, but in some of the runs we dialed the stellar feedback way, way up, so hopefully it would give, comparable amounts of energy. I realize that's an approximation. And then what we did was use isotropic conduction, so we're ignoring the magnetic fields and how that might direct the energy around. And then we took that Spitzer parameter and we just dialed it up and down. And so, because we can't simulate the magnetic fields in these simulations, we just assumed that there was some efficiency. And we went from full Spitzer down to our control run, which was no conduction at all. And then we did these 10 clusters with a bunch of different with a bunch of different conductivities. Okay, so what did we find? First off, we wanted to see, can you actually see the effect of conduction? Because simulations that were done, quite a while back at this point, which were much lower resolution and so on, showed that, oh my god, clusters, you turn conduction on and it's just night and day. And we just don't see that. And so, I put the numbers on here, unfortunately, but so you could probably guess, but these are two different galaxy clusters. One column is with the conduction all the way off, one column is conduction at the Spitzer value. And we're looking at a couple megaparsec region, and you see virtually no difference. If you look really, really closely at maybe the X-ray luminosity, you sort of see there are spots that, maybe the conduction is doing something, but maybe it's not. Who's to say? And it turns out that as you zoom in, you continue to see not much difference. And so I'm a little puzzled as to why this happens, why we don't see that much of an effect, and some of the previous people who have done this, again, several years ago, did, and it's probably a matter of numerical resolution. It might have something to do with the methods. It's hard to say. But when we start to dig into this and average the radial profiles from all of the simulations together, we see some interesting trends. And so these are average radial profiles from all of the clusters in our simulation, so trying to sort of tease out subtle effects. And it's density, temperature, and entropy. And you see the radial profiles, all mass weighted, colored by how much conduction there is. Black is 0, blue is full conduction, and then the other ones are in between. And then what we've done here is normalized it to the run with no conduction. And so what you see is that in these simulations, the density just at the center of the cluster goes down, but just outside of the center it goes up. So it's puffed up the core a little bit. And it's done virtually nothing outside of a couple hundred kiloparsecs. Similarly with the temperature, the central temperature has gone up some compared to our control run, and it's done pretty much nothing outside of 100 kiloparsecs. And so you see some effects on the entropy as well. When we zoom in, there we go. When you zoom in on the temperature, we do see one interesting thing, that on average, when you turn the conduction up to about 1/10 of the Spitzer value, you do see that on average, the temperature tends to isotropize in the center of the cluster, which is sort of interesting. So, but it doesn't make a huge difference, and we expected it to make a really big difference. And so I was quite surprised by this. And so then we wanted to explore the idea of conduction and how it affects gas condensation. And so we measured the amount of cold gas in the simulation, which essentially is to say we measured the star formation rate. And so this is the normalized star formation rate, so normalized to the simulation without conduction as a function of time. So this is a couple gig years after the Big Bang to the present day. And this is a scale, which I think the text might be a little small for people in the back, but it goes from about 4% below to about 10% above. And so the lines are the average of the 10 runs, and then you see there's quite a bit of variation. But even with a tremendous amount of conduction turned on, you get a little bit of gas condensation at the center of the cluster, a little bit of enhancement, but not a tremendous amount. And so, so generally there's a little bit more cold dense gas in the center of these clusters that's maybe helping feed the AGN. Okay.
Why do you get more with conduction?
Basically, it promotes cooling because you have a lot of cold gas at the center of the cluster, and essentially the heat is chasing the cold gas in, and so you just keep it relatively thermally unstable. So it seems to promote conduction. But again, it's an extremely mild effect, and so to me, this is it's almost a null result, which is sort of disappointing. So overall, we see that it doesn't do much, right? We get a small increase in the core temperature by conduction, makes the cores a little bit puffier, slightly enhances cold gas accretion onto the BCG or star formation. Maybe it would help AGN feedback. It's hard to say. But basically, what I'm saying here is that we need some other mechanism to move around cluster gas. It's just not working. And I think that what we really saw in our simulations is that when we really resolve the heck out of the fluid moving, the gas moving around in the center of the cluster, we see that the bulk transport of energy, essentially by turbulence, is way more important than conduction, which is a little sad. So I was hoping that this was going to be our silver bullet. Okay, so the next thing I wanted to do was talk about exploring thermal instability in cluster cores. And so this is, in some sense, exploring the anything goes now hypothesis. I really like that way of putting this. And this is a work in progress by Greg Meese, who's Mark's and my graduate student. But basically, what we're doing is trying to understand the heating and cooling of cluster cores. Now, Frank made the statement that simulators can now do whatever the hell they want. I like that as a simulator. I don't like that as a scientist. But really, the question we're trying to answer here is how much does energy deposition into the center of the cluster, how does the precise form of that affect the core and affect sort of how gas is heating and cooling and how it affects the creation of a multi-phase medium. And so the nice thing is that we can do some idealized simulations and then use them as an input for cosmological simulations. Because really, because cosmological simulations require you to simulate a huge dynamic range, we're never going to get below a couple kiloparsecs in resolution, at least not if we want to go down to redshift 0. And so, maybe not never, but it's going to be a challenge. And so we can't resolve a lot of this multi-phase medium in cosmological simulations, in my opinion. So we need to come up with some approximation for it. So the hypothesis that we want to test is, can the gas that's in global thermal balance in the central cluster core, because it does seem to be roughly in thermal balance, can you get a multi-phase interstellar medium based on the local cooling time? And also, how much is it?
Intercluster, or
what did I say? Intracluster.
Yeah.
Yeah. Did I say interstellar? Well, we'll go intracluster, because that makes more sense in this context, doesn't it? And so, and hopefully, this is a result that is robust to the exact structure of the intracluster medium, the exact structure, how we put feedback in, and so on. So, can we test this idea of anything goes?
4 minutes.
Oh, good Lord. Okay. Okay, so what we ended up doing was a bunch of idealized simulations. And so this was pretty interesting. So what we ended up doing was setting up simulations of stratified media based on some work that McCourt and Sharma and Quadert and some other folks have been doing. And what we did was 2D Cartesian simulation, so essentially just a stratified medium, not unlike the Earth's atmosphere, cylindrical, and then three-dimensional spherical. And so one of the thoughts that has been going around as we've talked to the other people that are thinking about these things is that the geometry might be really, really important. And so a lot of people are doing experimenting with just Cartesian calculations, and maybe the fact that when you do it in a cylindrical symmetry or spherical symmetry, gas gets funneled into the core makes a substantial difference. And so we wanted to explore that. Also, we wanted to create a medium that we could easily control, as opposed to cosmological simulations, where you don't really have a lot of control. And so what we did was created a bunch of density and temperature profiles that essentially were always initially in hydrostatic equilibrium and thermally stable at the outset. Well, I have to take that back, actually. So always in hydrostatic equilibrium at the outset, and then we let the gas cool, and we also heated the gas. And we heated the gas in a variety of different ways, but we ensured that globally, heating balances cooling, because that's what seems to be happening in galaxy clusters. And so then what we did was essentially just dial in the properties of the cluster by changing the ratio of the cooling time to the freefall time, which is essentially a nice way of saying we dial up and down the density and change the profile of the gas, the density and the temperature profile of the gas, to get isothermal or isentropic or constant ratios of cooling and freefall timescales everywhere, things like that. And so this builds this really nice laboratory for playing with this idea of feedback. And so here's what we see. So the lines, the numbers up here are the ratios of cooling to freefall time. So up here, the cooling time is very short compared to the freefall time. It's a tenth of it globally over the entire, everywhere at every level in the simulation. And then here, it is about 4 times the freefall time. And so one would naively expect condensation to almost immediately occur when the cooling time is short and not when it doesn't. And lo and behold, that's exactly what happens. We're looking at the baryon density, by the way. And this is a simulation where we're looking at a couple scale heights above the midplane, and everything should fall towards this line in the middle. And sure enough,
is what exactly? It's a shear flow, or just?
It's not a shear flow. It's just an initially stratified hydrostatic medium, and then we, at time 0, essentially just say, now go, and let it do what it's going to do. And so it's being heated, so it's cooling, and it's also being heated to totally offset the cooling globally, okay? And so, but that doesn't necessarily mean locally, as Christoph said earlier, right? So what we do see is that you get a multi-phase medium forming, and depending on exactly how short the cooling time is relatively, so how dense the gas is, sometimes it runs away, and sometimes you get something that looks an awful lot like convection, which is not a shock, where there's very, very little cold gas. And then over here, where the ratio of the cooling time to the freefall time is basically 1, it's a little bit more ambiguous what's going on. And so these movies are sort of interesting. You can kind of watch them over and over. Not that we're going to. And then you can do this in cylindrical symmetry, but I'm basically out of time, right?
Yeah.
So,
How
okay.
do you maintain this balance between heating and cooling?
I will address that in 1 minute. Why don't you ask me in the questions?
In 30 seconds.
Yes. So, All right, let me get to my main points. So when we're experimenting with this multi-phase medium, what we find is that if the cooling time is short compared to the dynamic time, we get a multi-phase medium. That's not a surprise, even if globally heating balances cooling. So that's fantastic. We also found that whether this happens or not depends on the local ratio of the cooling time to the free fall time. Also, that's not a surprise. Now, what was really interesting is that the rate at which this gas is created is only somewhat affected by geometry, so planar versus cylindrical versus spherical and so on and so forth. But what we did find that really is upsetting is that the rate of the creation of accretion, the rate of the formation of this cold gas and its falling down to the midplane depends really significantly on how the feedback occurs. So, well, how you put in the feedback and also the structure of the gas. So, what I'm going to say is, my main point here, so thermal conduction, blah, 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 but this multi-phase medium isn't a particularly robust problem. It turns out that what happens depends a lot on how you put the energy in. And so I think that's a good thing, actually, because what it means is that anything does not go. Thank you very much. I'm sorry, Nick, you asked the question that I didn't answer.
Nick.
I'd like to re-ask it.
Ask your question.
I already did.
Did I
Did
answer?
you get an answer?
Yes.
Are you happy?
You asked, what did you ask? You asked, how do we
I
put in...
asked well, obviously your cooling happens on a Planck scale, so depending how you balance global cooling and global heating, that will
Right.
be a different result depending on how you do this balance.
That's right, absolutely. And so, at present, what we're doing is we're just putting thermal energy into the gas. We have some ways of putting kinetic energy in, but,
Exactly.
Right, so there are several ways that we did it. The simplest way was essentially in that stratified medium, at every row of cells, so at every height above the center, we measured the total cooling rate, and we just ensured that on a level, heating plus cooling as a function of Z always adds up to 0. And that turns out to, any instability or any perturbations that you have immediately get magnified. It depends on the rate at which this happens, depends on whether you assume that the heating occurs equally per volume or equally per mass or equally per inverse volume. There's a bunch of different ways that you can do this, but it's always unstable. You can also experiment with having the cooling and the heating lag each other. So in other words, if you think that the initial condensation powers your AGN, which, so however many tens of millions of years later, then puts the heating in, you can also do that, and you see similar things. I mean, qualitatively, basically what happens is, if it's going to go thermally unstable, it goes thermally unstable, and no matter how you put the heat in, you'll never stop it. The details matter quite a bit, though. The amount of gas that goes thermally unstable depends a lot on how you put the heat in, how and when.
Okay,
So,
Joel.
Yeah, so going to the first part, conduction.
yes.
A number of people have worked on this,
Mhm.
and conceptually, at least for clusters, it looks like it should work because you have this infinite thermal bath beyond the cooling radius,
Yes.
and all you need to do is get the energy in.
Mhm.
The problem is that the observations show that you see a temperature decline in the inner part.
Mhm.
And if conduction is very efficient, it just blows away that temperature gradient.
Yep.
And you don't get any cooling at all.
Mhm.
And if conduction is not very efficient, then it doesn't do anything. It's not. So why don't we get that result, which is kind of what everyone else.
But that's roughly what we get,
No, it
right?
isn't.
I mean,
You
we
get
see it makes...
enhanced cooling when you have more conduction, whereas
Right.
everyone else gets no cooling when you have very efficient conduction.
Right.
Which is what you would expect. You're putting.
You get
Yeah.
some cooling onto the very cold gas, which probably
That's
wasn't in there. That's like ISM temperatures you guess that from.
That's right. Well, I mean, down to below 1,000,000 Kelvin, certainly. I mean, I guess there are several things that are different, right? So we're looking at relatively low mass clusters, right? We're not looking at 10 to the 15 to 10 to the 15 solar mass clusters, right? So some of the original simulations, and in fact the DOLOG stuff, was done with pretty massive clusters. And so when
Well, so
we...
there's a temperature at which the conductive heat flux
Sure.
is no longer adequate. As you go to lower mass clusters and eventually individual ellipticals,
Right.
becomes irrelevant.
Mhm.
But either it's irrelevant or it's really, really important.
Doesn't it
Yeah.
always produce the best it can ever do? Is produce a t to the 7/2 or drop linearly with distance. That's all it can do.
Mhm.
Because if it goes any flatter than that, the conduction is going the wrong way.
That's right.
So, you get this very flat gradient, which is why you've got a very slight increase. But you can never do a lot because if it goes up more, it's working the wrong way.
Right. But I mean, I guess to answer your question, I'm not really sure because there are so many differences between the simulations we've done versus the ones that have been done previously.
Yeah, but
Yeah.
this is fun, basic physics. If you're putting a lot of energy in, you blow away the temperature gradient.
Mhm.
We see a temperature gradient.
Okay,
I'm not sure.
Okay, never mind.
I'm very
Really
sorry.
not sure.
Once again, Joe, is your question short?
Pretty short.
Okay, short question, short answer.
Remember, we're
And we have
keeping
a
everyone
poster.
from coffee, so go.
We have a poster too.
Don't your 2 points somehow talk to each other? Conduction is
Yeah.
proportional to temperature gradients. So
Yep.
if you form a bunch of small scale cool structure, then you enhance the rate at which you conduct into those structures.
Yes, that's absolutely right. Yeah.
So, I mean, that may also be the issue. I mean, Joel, you're referring to observations. It could be that in the observations there's more cold structure to conduct into, right? Whereas in these simulations, those cold structures don't exist. Those temperature gradients.
Conductivity is going like up to 5 halves, that basically, it becomes weaker and weaker.
Yeah.
It becomes irrelevant.
Well, no, but the temperature gradient, if you have lots of cool stuff, then you have lots of hot, cold. You know what? Let's talk about it during coffee.
Good.
So,
Okay, thank you very much, Brian.
poster slide, I promise.